Yeah, so who is this dude? He's not Pythagoras. Who is he? Pythagoras. There he is. He's like toga and everything.
That's how you say it.
Pythagoras, right? And so his deal is the Pythagorean Theorem. We've used Pythagorean Theorem because you kind of need it for the distance formula. You know, I don't think they have us teaching this in the correct order. We should teach this first and then the distance formula. So we're a little bit ahead. A squared plus b squared is c squared. So Pythagoras did not really invent this. This existed. They knew about this. The ancient peoples of the world, the ancient civilizations did know about it. They didn't know why. They didn't care why. They just knew if I was building a pyramid or whatever and I needed something nice and level, this kind of a relationship worked out. So it was Pythagoras is like, wait, we've got like a theorem here and I can prove it. He did all these kind of cool things with it. So he kind of was formalizing it for us. So what do we have here? Okay, Pythagorean theorem, let's get to it. And it is a biconditional. The converse will be true as well. In a right triangle, the square, not the roots, the square of the length of the hypotenuse is equal to the sum of the squares of the length of the legs. So a lot of words there to basically say a squared plus b squared equals c squared, where c is the hypotenuse and a and b are legs of a right triangle. And this is if and only if. So if a squared plus b squared is c squared, then you have a right triangle. And if it's a right triangle, then a squared plus b squared equals c squared. So here are my legs, here's my hypotenuse. A squared plus b squared is c squared. We always look at c as our longest side, our hypotenuse. So far, nothing really new. To prove this, there's all kinds of proofs for the Pythagorean theorem, tons and tons. Even President Garfield wrote a proof for the Pythagorean theorem. Yeah. So it's nice to have a mathematician, in office, even though it's got a little short for him. But anyway, so here's kind of a famous one that you tend to see a lot, where they'll take a right triangle, and this one is 4 units long, this side, and this side is 3 units long, and this side, the hypotenuse, is 5 units long. And so they basically set out to show, if you square 4, you get 16 boxes, right? And if you square 3, you get 9 boxes. And if you square 5, you get 25 boxes. And it works. A squared plus b squared does equal c squared. Now what's the problem with a proof like this? What's the issue, Jeff?
The boxes are slightly different sizes, or and
well,
you don't know.
we're saying, we're going with the work that these are true squares. All this is correct. There's nothing incorrect about this. It's correct. But what is the problem about using this as our proof? What's the problem with it? No, not necessarily. Amanda, what do you think?
It already has the solution given, but maybe it doesn't really exist in all right triangles. So
maybe it doesn't work for all of them. This is very inductive, isn't it? It's basically saying, well, because it works for this, it must work for all of them. So this is an inductive type proof, which, that's not bad for coming up with a theory. I think, here's a conjecture based on this, that a squared plus b squared equals c squared. And many of the proofs that you see are kind of like this. They do variations of this, but we need something more deductive. Yeah? No, this is not. I don't have it all on hand, but it was a similar kind of idea. So I went around and I said, that's not good enough, because we're in geometry now. We're not really just looking at inductive. We need deductive. So here's another one, and this is not President Garfield's proof either, but I think it was something like this. So basically, I've got a figure here. It is a square, because each side is a plus b units long. So it is a square. All the sides are the same length. And within this square, I kind of made another square in here, where each side is c units long. And because of that, I have these right triangles. And you see these right triangles on the edge. And this one is length A, and this one is length B. And so they're kind of equivalent triangles all the way around, aren't they? Right, because they have those same kind of side lengths. So what we're going to do is we're going to kind of compare the area of the big square with itself. Like here's this large square, right? Do you remember what can you find the area of a square? It's side squared, right? If you know the side of the square, you square it and you get its area, right? Like this, yes, not up and down. Okay, good. So that means if I want the area of this entire square, what is the length of a side? If this piece is A and this piece is B, using segment addition, what would be the length of the whole side, Joseph? It's A plus B, right? And so this one's also A plus B. All the sides are A plus B. So if I want the area, I just do a plus b times a plus b, right? Wouldn't that give me the area of this whole thing? Okay. Now another way to think of the area is to kind of find the area of all the pieces. So we can do that too. So if I want to just get these triangle areas, working on this part first, how do you find area of a triangle? Area is 1/2 base times height, right? And we learned before that altitudes are height. And I know this is an altitude because I see that right angle. So 1/2 base times height. So each one of these triangles has an area of 1/2 AB. 1/2 AB, 1/2 AB, 1/2 AB. So I'm going to say, to find the area of just the red pieces, I take 1/2 AB, and since I have 4 of them, I multiply by 4, and then this will cancel out. 2AB is 2AB. And that's just the pink or the red pieces. 2AB. I still have another piece, right? What's the area of the blue? This side is C and this side is C, so what's the area of the blue piece? C squared. So let's see what we got here. The area of the smaller square is C squared. So I'm going to kind of compare these things. The area of the large square is A plus B squared, but it's also all the red pieces plus the blue piece added together. These are all the red pieces, and this is the blue piece. You follow so far what I'm doing here. Basically adding up the pieces, saying it's going to equal the whole thing, right? Okay. Oh, yay, algebra, here it comes. I need to square this binomial. Remember how to do that? Squaring A plus B?
Yeah.
It's not A squared plus B squared. Let's expand it. You're going to remember FOIL, or that thing.
Oh, I totally love
Yeah.
it.
So you do, or multiple distribution. A times A is A squared. A times B is AB, right? Then I do this one. So it says BA, I'm going to rewrite it as AB. And then I get my B squared. These are like terms. I've got 2 of these ABs. So that's using our friend algebra. And so that's going to equal this side because they're both this area of this entire figure here. Well, look what I can do. I can subtract out 2AB from both sides. Sure can. And then what am I left with? A squared plus B squared equals C squared. Woohoo! We did it. We proved the Pythagorean theorem in a much more deductive way. So many of these proofs are kind of variations on this thing, but I feel better now. We can use it. It's proved. Prove it. Yeah. Okay. So if I want to find missing sides, and this is kind of near the topish of the front page here, I'm going to use A squared plus B squared equals C squared. And A and B are legs and C is hypotenuse. So the first thing you need to do is figure out where your hypotenuse is. It's still the side across from that right triangle. So this is your H, or what we're calling C. Who's A and B? Does not matter. At this point, you can call either one of these A and B. The important thing is which one's C. So A squared plus B squared equals C squared. So we'll substitute in our 8 for A and our 6 for B. And X is our hypotenuse. Okay, now we gotta figure this out. So that's 64. And that's 36. 64 plus 36. Last time I checked, that was 100. Now be careful when you solve these. X squared equals 100 actually has 2 solutions. What are the 2 solutions to x squared equals 100? Amanda, what are they?
X equals 10 and x equals negative 10.
Exactly. Plus or minus 10, because negative 10 times negative 10 is also 100. And so you can't just say, oh, it's just a positive. It's both. Now we're going to reject the negative 10 because it doesn't make sense in this situation because we're looking at sine length. So most of the time we are going to reject that negative solution, and we tend to take that shortcut and just say x is 10. I do want you to kind of remember somewhere in the back of your mind that you really are finding 2 solutions and one is being rejected. But meanwhile, look at the side, 10. And here I've got a leg that's missing, right? Because here's my hypotenuse, right? That's my C. And either one of these is A and B. Does not matter which one. So A squared plus B squared equals C squared. I'm going to substitute in the values that we know. So x squared plus 9 equals 25. So far, so good. Subtract that 9 from both sides. 16, yeah? plus or minus 4, we tend to take the shortcut when we're actually looking for side lengths of just saying it equals 4. But we do understand there is a negative solution as well that we're kind of not using because it doesn't apply in this case. X is 4. Awesome. All right, so same kind of thing here. My hypotenuse is the side opposite, so that's my C. Either one of these is A and B. A squared plus B squared equals C squared. X squared plus Y squared equals 10 squared. X squared plus 25 equals 100. I'm going to subtract that 25 from both sides. And so now I don't have a perfect square. X is the square root of 75. I can reduce this, right? Because this is really the same as 25 times 3. And 25 is that perfect square factor I was looking for. So this is going to be 5 square root 3. Unless told otherwise, or it's a word problem, we tend to go to our simplest radical form, our exact answer. If it says find the exact answer, that's this. If they want an estimate or they say round to the nearest 100, that's when you would put it in the calculator and give me a decimal. But if you're not sure, I want the simplified radical form for these sides. So easy peasy, right? What I often do when I see it's one of these, I use the reverse, not the reverse, but an alternate way of looking at this. So C squared is A squared plus B squared. Let's say I want to find one of these. So then A squared is going to be C squared minus B squared. And A is square root of C squared minus B squared. So after you've been doing these for a while, you may automatically start just going to this. Oh, if I want this, I'm going to take the square root of that thing, the square of that minus that. Square root of the whole thing. You'll see as you do these 100 times that it becomes easier to maybe not write this out each time, but kind of go directly to this. So anyway, why do we do things like this? To do real life situations. So here's another, again, classic kind of geometry problem, the ladder against the wall problem. It's right up there with flagpole and tree height. Ladders against the wall. You need to know how high up the wall that is. So we've got a 16-foot ladder, and it's against the side of the house, and the base of the ladder is 4 feet away from the house. And of course, everything's perfectly level. So we have a nice right triangle with the wall to the floor. So we can kind of see our triangle here, I hope. So this is my right angle. So in these pictures, you do need to kind of identify where would that right angle be. Here's my hypotenuse, it's the side opposite. This ladder length is my C. And so one of these is A, one of these is B, whichever one you want. You could write this out as an A squared plus B squared equals C squared, and make your substitutions. And then I will actually do all the squaring and stuff when I'm done. So if you kind of do them this way, eventually you will be able to leap right to kind of this step and save a little bit of computation once you get used to working on it. So what do we have here? That is 256. And that's not 14, that's 4. 16 times 16 is 256 minus 16 equals the square root of 240. Oh, goodness gracious. So, like, if I wanted the exact solution, I believe this comes out to 4 radical 15. Is 16 times 15 240? Somebody check for me. I think it is. Yeah, so, I mean, that would be exact. Now, with word problems, you're going to tell somebody, yeah, Joe, I got the height. It's 4 by 15 feet. Right? And never, right? In word problems, generally speaking, it's usually okay to go to the decimal. So, I'm not that good. I don't know what it is. So, let's see. Square root. Let's see here. That's this one. I'm going to go with this one in case I made a mistake in the reduction. So, I'll go here. And it's about 15.49. And again, C, we probably wouldn't say it was 15.49. If we're being, like, real picky, we might say 15.5 feet. So, the rounding, do look and see what it tells you how to round it, but also use common sense in how you would round it. With the word problem, think about what you would say when you real life. So, about 15.5 feet high. So if you ever need to know that, now you know how to do it. I think I have another word problem here. There's another example here with an isosceles triangle. So you've got to want to find the area of an isosceles triangle with these sides. So your equal sides are 13, and I'm going to put my little marks there. and your base side is 10. So we want to find what we've got going here. So area of a triangle is 1/2 base times height. So in this situation, here's a height, right? It's an altitude. So that would be my height. And I'll write it out so it has to be confusing. And this 10 is my base. And somehow I'm telling you that this is 5 and 5. Now why would that be? Let's think about what we know here. It's an altitude, right? You're telling me this is the height, so if it's 90, it's 90 here too, right? And I also have this kind of thing, and I also know these are, and I'm just trying to see what I know. Because if I can get these two triangles congruent, then I know these two pieces are equal, right? Do I have congruent triangles? How come? Did it say that it's single bisector? Well, we can figure it out, but I don't know it yet. No, just because, no, not necessarily because of that.
It is because.
But it will be because of why? We do have an angle side. We also have hypotenuse leg. These are congruent triangles. Now I can say with confidence, yeah, you're right. But I didn't necessarily know that ahead of time. CPCTC. Also, this congruent to that by CPCTC. Yes, sir. I did not know that these sides were congruent. I do now. Well, they're telling us that, and I was like, why? Because they don't always give you that information. They sometimes will say, here is an isosceles triangle. So they will be congruent, but you know, we proved it right now, so now you can use that. So they are going to be the same.
Why do we need to do this?
Well, I need to find out the height.
It's just Pythagorean theorem.
Well, but I don't know what these sides are, and I can't use Pythagorean theorem unless I know what the side lengths are. Okay? So I have to know that these are 5s. That's what I do. Because now, what?
It's labeled though.
Yes, but what if it wasn't? I'm making this problem slightly more interesting,
If it
which is
wasn't labeled, there would be no way to tell. Because if that
so. How
Well,
what works?
proof those two.
We did hypotenuse leg that these two triangles are congruent. Therefore, this side is congruent to this side by CPCTC. If the whole thing is 10, then each of these is 5. Now I can use Pythagorean theorem because I need to find this height. So where is the hypotenuse? That's this 13. So my height, and let's just call it x because now we got too many h's involved. So this squared plus that squared is that squared. So my x squared, which is my height squared, plus this little 5 millimeter or 5 meters squared is going to equal 13 squared. So that means that x squared is 13 squared minus 5 squared. And that means that x is the square root of 13 squared minus 5 squared, which is going to be 169 minus 25, which I think that's 144. Check my work. Yeah, she said yes. Square root of 144 is 12. So that means the altitude here, this height is 12. So we can find the area. Area is 1/2 base times height, which is 1/2 my base is 10. And we just figured out the height is 12. Half of 10 is 5. 5 times 12 is 60 square meters. Is there a question? I'm going to sign a hand up.
Yeah.
Yes.
So why would it be 5 or would it be 10?
Which?
For the base.
The whole base. So like it's this triangle, right?
Yeah.
So this is the base of 10, and here is the height of 12.
Okay.
So, and it's a height because it's the altitude. So that's what we're using. We use the fact that it did kind of bisect this side to find that 12. Yeah. Okay, good. So yeah, so it's little applications using this this Pythagorean theorem. Now Pythagorean triples, they are ways of kind of speeding up this process of finding missing sides. So Pythagorean triples are 3 positive integers. You have to know what an integer is, right? What's a positive integer? Amanda, what's a positive integer?
Positive integer is a whole number that is above 0.
Okay. Another name for that, I guess, would be natural number. Right?
I never got why they didn't just say whole
1, 2,
number.
3, blah, 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 right? So positive means not 0, because, that's never. So
Or not below zero.
such that a squared plus b squared or c squared, there are 3 numbers that satisfy the Pythagorean theorem. So an example of Pythagorean triple is 3, 4, and 5, because 3 squared plus 4 squared equals 5 squared. That's my claim. Well, let's make sure. That's 9 plus 16. Does that equal 5 squared? Yes, it does. That's 25. So it matches. So this is a Pythagorean triple because it works. Which would be the hypotenuse if I said these are the sides of a right triangle? Joseph? It's always the biggest side. That's going to be your hypotenuse. So these are the legs and there's the hypotenuse. That's your C. So a primitive triple. Oh my goodness gracious. A primitive triple are ones like this, where the sides are co-prime. And what co-prime means is that there's no common factor in here other than 1 for these 3 numbers. Co-prime. That's a primitive triple. Now you can have other triples that are not primitive by applying a scale factor. So if you multiply all of these numbers by 2, you get 6, 8, and 10. So the scale factor I applied was 2. This is still a Pythagorean triple. It's no longer primitive because it has, that common factor of 2. But it's just like this one, only twice as big. And it is a triple, a Pythagorean triple. So, what have we got here? Yeah, there it is, 6, 8, 10. You can multiply it by 10, 30, 40, 50. That's going to be a right triangle. It's going to be a squared plus b squared is c squared. It's going to work. You can try it if you want. So you can take a primitive triple and multiply each one by a common factor to get another triple. So for what? So what we do with these, and we'll do this in a minute, but what's the good part about it is if you know these are some primitive triples, there's a whole bunch of them, then you can find other triples, and if you see a triangle that is maybe missing a piece, like that says 15 and that says 20, I know that that third one's going to be 25. I don't have to keep doing the math over and over. So to generate this table, the scale factor, it basically says multiply, this by 2. So this one becomes 10, 24, choices. Then multiply it by 3. I'm probably going to make a mistake doing this. And then you get a whole massive table of it. Take a moment and see if you can fill this table with a whole bunch of triples. Primitive triples are across the top, though. Somebody said, so I have to memorize all these? I have to memorize all these. I mean, I would never be able to do that. What's good to know, though, are these. So if you can remember some of these primitives, and there's a bunch more, and I'll be honest with you, the ones that I see over and over tend to be these two, but you will sometimes see the other ones. It will help you kind of speed things up. So how do we do that? I forgot about this. This is kind of a cool way that I found if you want to kind of create some triples. This is like why you take my class, because you get these little extensions here, a little enrichment. Let's say you want to create a triple. You can actually use this little formula. So if you take 2 numbers, let's say I'm taking 9 and 5, and I want to create triples. So first thing you do is you multiply them. The next thing you do is you take the difference of the squares, a squared minus b squared, and you do want to, order them so that the bigger one comes first. You get 81 minus 25 over 2, and then you add them, those squares. Okay, what do we get here? So now I've got 45, 81 minus 25. I want to say 56. Is that right? And 81 plus 26, that looks like 127. Is that right? No. 106, that's a 5. 106 over 2. And so that gives me 45, 56 over 2. That goes twice, that's 28. And then this one becomes what, 53? So order them smallest to biggest. Is this a triple? Did I just create a triple? Let's see, 28 squared plus 45 squared. Is that the same as 53 squared? So I to me, stuff like this is cool to me. So I just thought it might be cool to you. If you
That's
ever
so
want
cool.
to find a Pythagorean triple, you can use this little formula. Yeah. It is proved up, and I'm not proving it. I'm not doing that. But yes, somebody did prove it, because otherwise I wouldn't be able to use it. Yes. I don't. And if you want, you could probably look this up. Just Google this formula, and it'll probably give you, I found it somewhere, I Googled something, I can't remember what, but I was like, wow. You could probably say generate Pythagorean triples, and you might get some cool story, an article on it that explains that. How cool is that? So there's tons and there's, I think, an infinite number. Somebody may have proven there's an infinite number of these, which is pretty cool. So anyway, how do you use them? What's the point, right? So suppose you have a right triangle and these are the legs, 20 and 48. So you got some kind of right triangle and these are the legs. And they want you to find this. So you could do 20 squared plus 48 squared and find the square root. Or you can do this. Look for the greatest common factor of 20 and 48. And I'm on the back here. I'm at the top of page 2. Hopefully you're following along here. The greatest common factor of 20 and 48. Yeah? What is it? I think it's 4 too, isn't it? I think it's 4. So what you do is you divide by 4. Greatest common factor is 4. So 20 divided by 4 is 5. And 48 divided by 4 is 5. So you kind of would take the little triangle and say, okay, divide by 4, common factor. So that one is going to be 12, and that one's going to be 5. Let's look at our list of primitive triples. Do I have any with legs 5 and 12? Yeah, 5, 12, 13 triangle, right? 13. Okay, so that's really a 5, 12, 13 triangle in disguise. But it's everything multiplied by 4. So once I know it's 5, 12, 13, and it's a multiple of 4, I'm going to multiply this piece by 4. So 13 times 4, 52 is my third side. It's 20, 48, 52. I don't have to go through the pain of Pythagorean theorem. I guess if you have your calculator, the pain's not too great. If you don't have your calculator, you can just do this. And back in the day, 175 years ago when I took geometry, we didn't really have calculators. So this was really useful. But I tell you, now we get very, I don't want to say lazy, but it's really fast. If you get good at this, you can find those third sides really, really fast, much faster than using that calculator. So like if I'm using like some of these little, we did these examples before. So 6, 8, so we could use the Pythagorean theorem, and we did. And I think the answer was 10, but we can also say like 6 and 8. Common factor of 2, so let's divide by 2, and I get a 3 and I get a 4. 3, 4, what's the other side then? Look at the 5, right? We have a 3, 4, 5 triple. I divide it by 2, so I multiply by 2, I get a 10. It's just a fast way of getting there. Yes?
But with today's technology, you can do a whole bunch at once by inputting the numbers and.
If you want to write a program to do it, fantastic. But very often, if you're doing a real life problem and this comes along, you're like, oh, what's that? I mean, first one you're thrilled. You're like, whoa, I can use the Pythagorean theorem. And if I saw 3 blank 5, I'm just writing it in. I don't take that. How much faster can it be than that, right? They don't always work though. Like, let's try this one. So I do 5. Oh, okay, it's got a 5 is common factor, right? So that's a 1, and that's going to be a 2. I don't have a triple for that. So if I don't have a triple, then I would use the Pythagorean theorem. I mean, I think this one came out to 5, that too. So yeah, it's handy. It is handy. Is it worth learning? I think it is. You do have your calculators. You don't necessarily have to. It's a really nice check. It's a really nice way of understanding what I did is right. It's a kind of a cross check. It's a fast way to do it. So let's try these. I'll just do the first one again, so remind us how to do it. So if you have a 27, a blank, and a 45, you look at 27, you look at 45. What's the common factor? So divide by 9. 27 divided by 9 is 3. There's my blank. That's a 5. 3 blank 5. What's my primitive triple? Look at the little table, right? Do I have 3 blank 5 triple? 4. Multiply that by 9, and there it is. So give these a try. What? Definitely. so here's what I got. Now you could have used just straight Pythagorean theorem, you will get the same thing. This one I noticed common factor of 4. So this became a 24 and a 25. So that's a 720, sorry, 25. 724, 25, so multiply by 4, you get the 28. This one, I think it has 13 as a common factor, am I right? So that became a 5, a blank, and a 13. So that's a 12. 5, 12, 13. Multiplied back by 13, I got this. This next one, I think, has 7, right? Common factor of 7. So it became 724, and then what comes next? 724, 25. Multiply that by 7 to get back here. So you don't even need to do the Pythagorean theorem if you recognize a triple. So that's the whole point of that. You just kind of keep that in your back pocket. Alrighty. Classifying trials based on, okay, this is kind of neat. A squared plus b squared is c squared. In all these examples, c is representing the longest side of the triangle. So we know this. This is our Pythagorean theorem. A squared plus b squared is c squared. You have a right triangle. That was an if and only if. So yes, got it. However, if a squared plus b squared is bigger than c squared, this angle over here that used to be right, now it's a cube. So we're kind of thinking it's not a hypotenuse anymore, but it's sort of in that same position where it would be if this was a right angle. And think about that. These got longer. So it's kind of like they, I don't know, they're leaning in a little bit, so this gets shorter. And if a squared plus b squared, you square those and add them, and it's smaller than c squared, this is bigger than the square of those sums, then you have an obtuse triangle. So it helps you figure out what kind of triangle you have. Now, how do you remember all this? I usually hate little things like this, but I'm doing it. What can I say? So if you have a squared plus b squared, and it's greater than c squared, see how my greater is kind of pointing to the c? It's a cube. And normally I hate stuff like this, but I'm giving you one. If a squared plus b squared is less than c squared, see how it's pointing to the b? So that one is obtuse. Okay. What? Oh yeah, the other thing is you have to know that you have a triangle. So let's just do a couple of examples so you know what I'm talking about. So I've got these numbers, 22, 43, and 49. And first of all, is that a triangle? How do I tell if I have a triangle or not? Amanda, how do I tell?
You tell them to triangle, if it's a triangle or not, by seeing the first two sides added together are more than the third side.
Where this is the longest side, right? You're talking about the third
Yeah,
side. So it's always a good idea. Why not order them smallest, medium, large, right? And if you add these two and it's bigger than that, it's a triangle, right? So is 22 plus 43 bigger than 49? Yes. Okay, so yes, we have a triangle. Okay, now if it is this a right triangle, an acute triangle, or an obtuse triangle? Okay, so yeah, that was yes. Number 2. So let's see, let's find a squared plus b squared. So a squared plus b squared is 22 squared plus 43 squared. I'm going to use this. 22 squared plus 43 squared. Hopefully I'm entering this right. I am getting, what do I write out there? 2333? Okay. And let's see what c squared is. C is 49, right? So I'm going to square that. 2401. So here's my a squared b squared. Here's my 2401. 2333 and 2401. So do I want a less than, greater than, or equal to? 233 and 2401. Is that less than, greater, or equal of those here? No. It's the less than, right? 233 is smaller than 24, and it's a less than. And where is it pointing to? The B. It's an obtuse triangle. Yeah. So it's a little way to figure out what kind of triangles you have. So let's just do one more little example here, like 4, 9, and 12. Make sure that they're ordered kind of small, medium, and big. 4 and 9 is 13. It's bigger than 12, so that is a triangle. So if that that's your a squared plus b squared. I kind of make two columns, my a squared, and my c squared. So that's going to be 4 squared plus 9 squared, and that's going to be 12 squared. That's 16 plus 81, and that's 144. And if I add 16 and 81, I get 97 and 144. Then I look at this. Is it a less than or greater than or equal to? That goes here. Still with me?
Yeah, I'm just.
You're working ahead. Who's kind of with me and just kind of watching it? What goes here?
Passive
What goes here?
observer.
Thank you. A less than. So a squared plus b squared is less than c squared. What kind of triangle? Yes, sir. Obtuse, thankfully. It's pointing to the B. It's obtuse. Try these over here. Right? So, and then 4 is about 2 times squared. So you're going to square the 4, that's 16, and you're going to square the radical 2, that's 2. So this is really 16 times 2, right? 32? To get 36, and I think we can see we're going to be bigger there. This is 46. Bigger than 36 is pointing to the c squared, right? That's your a squared plus b squared, and that's your c squared, so this one is a cube. Now this one, a lot of people have twos, because you went through the work, right? But there's one step I guess we do, and maybe I did it wrong, it's possible. I said, let's see, 5 and 10, well first of all, I didn't even know, is this in order? What is the square root of 230? I don't know. So let me find out what it is. It is the square root of 230. Approximately 15 point something. Approximately, say 15.2. Well, that means that we add 5 and 10, that's only 15. It's smaller. This is the example of, remember we had Tower Bridge? And it wasn't going to fit. And the buses were going to like fall into the Thames there. Yeah.
When I did on the calculator, it said that 4 red 2 squared root.
8?
Yeah.
Let's see.
Do 4 times.
Okay, 4, rad 2. Am I going to square that guy? Yesterday we multiplied something, or what happened? Oh, okay, so I think it did this. Or something, some bad happened. So notice like the parentheses, take that full unit and then square it. Or,
Oh,
remember that it's 4 squared plus
It's
square root
square the
2
root
squared.
2.
Yeah. Okay. Yeah, what do you think?